Hello, my name is Mr. Wilke, and we're learning statistics, but we're on to chapter 2. So once again, we're presented with a whole bunch of data that means absolutely nothing because nobody put a title on it. Also, it's really unorganized, isn't it? I mean, I can look and say, I bet the mode is 2.1, but I don't know if this is something that requires the use of mode. So first thing I want to do is I want to put them in order, and I really want to know what these numbers represent. So let's do that with some magic. Aha! The Oakland A's 2020 salaries by $100,000. So this is $100,000. This would be $10,200,000 or 1.02 million. The highest would be 6.2 million. Okay, interesting. Now, let's talk about where a data point is. So maybe you've heard the term before, but let's talk about percentile. Okay, now we talked about percentile a little bit last chapter. We said that the median is the 50th percentile, the first quartile is the 25th percentile, and so on. So let's talk about just the pth percentile. Is the value with p% of observations less than or equal to it. Okay? Less than or equal to it. All right? Now, there are some places that define it as just less than, but the definition that we use is less than or equal. If it's discrete, it'll matter. If it's not discrete, it won't matter at all. So if it's continuous, the or equal doesn't matter at all. Okay? So now, let's say what would percentile, let's try this again. What percentile would a person who makes $1 million be at on the A's? Now, with percentile we say at, not in, okay? It's a nice distinguishment there. So there are 28 people on the A's, so 4 rows of 7. $1 million would be right in there. So there's 14, 15, 16, 17 out of 28 observations below. So they're right around being at the 61st percentile. Okay? Does that make sense? Easy enough? Is it always good to be in a higher percentile? I mean, it depends, right? If it was for height, if you like being tall, sure. If you don't like being tall, no. I think your book might give an example of having cholesterol levels. You do not want to be in the 99th percentile for that. Okay, so let's go back and keep this data. keeping these numbers, I want to talk about a way to graph this, showing where we're at, and the graph is called an ogive. It's fun to say. Ogive. Say it at home. Ogive. All right, anyway, an ogive is also called a relative cumulative frequency graph. Remember what relative frequency is, right? Relative frequency is just the percent. Cumulative means everything up to and including. So we're going to have a relative cumulative frequency graph. So let's look at our data. Now, this goes from 1.1 to 62. So we don't want to go by ones, right? So let's go by about, I don't know, eights. So let's go, and we'll do a frequency graph. So we'll go 0 through 8. And we'll do it minus, so just under 8, just under 16, and so on. So 16 to 24, 32. We need to get all the way up to 62, so 40 to 48. I mean, I could even call this 7.999, you know what I mean, right? Okay. 56 to 64, and that's as high as we need to go. So how many are in here? This will be our frequency. So between 0 and 8, there are 14, 15, 16. Between 8 and 16, 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Then 0, 0, 1, and 1. Okay, so those are our frequencies. Let's do our cumulative. Cumulative is everything up to and including. So 16 would just be 16. This would be 16 plus 4 is 20, plus 3 is 23, 26, and 28. Now, let's get, we could do relative frequency. Relative frequency would be 16 out of 28, which is 4 out of 7, so 57.1%. 4 would be, what, 14.3%. 3 would be about 10.7%. 10.7%. 0, 0. About 3.5% and about 3.5%. And if I add all these up with rounding errors, it should add up to 100%. So let's do relative cumulative frequency. So starting at 57.1%, add that, so that's what, 71.4%. That would be 82.1%. plus 10.7 would be 92.8%. So this probably should be 33.6. That's probably pretty close. Like I said, rounding errors, let's call that good. So this would still be 92.8. This would be 96.4% and 100%. So, to graph this, all right, I want to what's going to go, let's move that over. What's going to go on the y-axis? Relative cumulative frequency, that's correct. Relative cumulative frequency, what's going to go down here? Salary, we're going to start at 0. So we'll go up to 100%, 40, 50, 80, and so on. We'll figure that out. Salary, 8, 16, 24, 32, 40, 48, 56, and 64. Now, the way it's going to work, we're plotting these numbers, right? It's a relative cumulative frequency graph, so this is an ogive of the A salaries. Starts at 0. By 8, we were at 57.1%. So that's right about there. By 16, we're at 71%. It's about right there. 82%. 32, we're at 92%. And then it stays there. So we're here. So we need to go straight across, then up, and then at the end, 64, and it connects like this. Now, what does this show us? Well, it shows us that if I wanted to know where the median is somewhere between 0 and 8, right? If I wanted to know where the first quartile is, 25%, somewhere between 0 and 8. If I wanted to know where the 70th percentile, it's right here, somewhere between 8 and 16, and so forth, okay? Up here, 100%, that's where it all goes, right? So if we were to draw this as a relative cumulative frequency histogram, this would just be a bar that tall. This would be a bar that tall, and so forth. Does that make sense? Good, okay. If it doesn't make sense, stop and think about it for a while. Why does that work? What would these bars look like? There'd be no bar. These bars would be, what, 3.6%? Just like that. Okay? Any questions on this? All right, so that's what we call an ogive. All right, let's talk about linear combinations. Now, if it's a linear equation, if we were in algebra, we learned it as y equals mx plus b. In stats, a linear combination is a plus bx. So we're adding a number a, we're multiplying a number b. Okay? So let's think about this. If I looked back at the A's salaries and I said, I'm going to give them all a bonus That's nice of me. I'm going to give them all a bonus if they win the World Series. So let's say we're going to give them a, I don't know, a $300,000 bonus for winning the World Series. It's pretty good, right? That's worth it. So 300,000, that would be adding 3 to everybody's number. Now, let's think about this. If we add some constant A, what changes? What changes if we add something? Let's think about it. If I add, let's go back and look at the salaries. So this guy goes up quite a bit. This guy doesn't seem like as much, but they're all going up the same amount. So what's happening to the distribution? The distribution is just shifting 3 to the right. Does the shape change? It doesn't, right? Does the center change? It does. Does the variability change? Think about it. The center is the only thing that's going to change, isn't it? I mean, all the data points change, obviously, but the distribution overall, just looking at shape center variability, the only one that's really going to change is the center. Now, if we multiply by a constant b, what's going to change? Let's go back and look. Let's say I decide I'm going to double everybody's salary. Wow, okay. Well, and think about it. I mean, we're playing 60 games this year. It's regularly 162. Really, we should go multiplying by 2.7. But let's just look at it in terms of, I'm just going to double everybody's salary. This guy goes from, what, 110,000 to 220,000. This guy goes from 6.2 million to 12.4. That's definitely going to change the center, right? What's going to do with the, well, the median would just, everything doubles, the median would double. The mean would double. What would happen to the variability though? What would happen to the IQR? What would happen to the range? Well, the range would go from, right now it's what, 62 minus 1.1, so 60.9. If it was at 124 minus 2.2, oh, the range would double. So the variability is also going to double. So when we add, the center changes. If we multiply it by a constant b, what changes? The center but the shape still stays the same, doesn't it? Now, why do we need to do this? Well, let's think about it. Think to yourself, if Mr. Wilke said, man, it's 40 degrees out, would you think, wow, that's really hot, or wow, that's really cold? And I know you're thinking, oh, well, 40 degrees what? Exactly, 40 degrees what? If it was 40 degrees Celsius, that's pretty hot. If it's 40 degrees Fahrenheit, that's pretty warm. 40 degrees Fahrenheit is cold, sorry. 40 degrees Fahrenheit is cold. If it was 40 degrees Kelvin, I think it's just Kelvin, right? Yeah. Well, it'd be really, really, really cold. Really cold. Okay. So, but if we change from Celsius to Fahrenheit so Americans can understand it, well, what are we going to do? We're going to multiply by 1.8 and add 32. That's a linear combination. It's not going to change the shape of the temperatures of the data, but it is going to change, well, the mean. It is going to change the median by multiplying each by 1.8 and adding 32. Is it going to change the variability? Just by multiplying by 1.8. The adding 32, if we multiply by 1.8, it spreads it out by a factor of 1.8. If we add 32, it just shifts everything over. Okay? Does that make sense? Now, it gets tricky when you're multiplying. It has to be a positive number. Okay? Technically, you're supposed to square it, multiply it by the variance, and then square root it to change the standard deviation, but we're going to start out a little bit easier and just think of it as make sure it's positive. If it's not positive, make it positive. Okay? Because when you're multiplying by variability, well, it doesn't make, you can't have a negative standard deviation, right? You can't have a negative IQR. Right, okay, cool. All right, one more thing we got to talk about. Let's talk about z-scores. A z-score is a way of standardizing your data and it's going to be taking each individual x minus the mean divided by the standard deviation. So what this is going to tell you is how many standard deviations something is above or below the mean. So if a data point is above the mean, the z-score is positive. If it's below the mean, the z-score is negative. Okay, so we will look at things like this. We will do a lot more of this when we get into normal distributions, which we will get into the next time I see you. So, but for now, make sure you understand that z is each individual x minus the mean divided by the standard deviation. So let's say there was a data set. Well, let's say on the chapter 1 test, it was 72 with a standard deviation of 8. Okay? So let's figure that out. You want to get an A. How many standard deviations do you need to be above the mean? Well, let's find our z-score. Z equals 90 minus 72 over 8, which is 18 over 8, which is what, 2.25? So if this was the distribution, and you wanted to get an A, you needed to get 2.25 standard deviations above the mean. Now, if S was 70, or X bar was 70, S was 14. What z-score do you need here? Well, again, it's time to go 90 minus 70 over 14, which is 20 over 14, or 10 over 7, so about 1.43. Did I do that right? I think so. Okay, and that's it. All right, do we see how it works? So z-scores are going to show up a lot over the course of this year. So make sure you understand them at a very basic level now, and we'll get to more with them as time goes on. All right, does anybody have any questions? Okay, well, that's it for today. So again, thank you guys for coming. Thanks for listening. Thanks to Skullcrack for the shirt, and I will see you guys later.